Imagine a world where a surgical trainee can receive real-time guidance from a senior surgeon, no matter where they are in the world. No more delays in feedback, no more limitations due to distance. Training becomes immediate, interactive, and accessible. Introducing NextGenScrub. My name is Emen,
I'm Maria.
And I'm Malcolm.
and we will be presenting our project. We'll be going through the background, design challenges, our design process, things that went right and wrong, and finally conclude with our demo and future iterations or future developments.
So let's start with the background of our project. What is the challenge and what is the problem that we're trying to tackle? So, first of all, there is a shortage of senior surgeons in Canada. And this limits hands on training opportunities for up and coming surgeons because it makes it difficult to gain experience. This is because current training methods often rely on retrospective evaluation. This means that feedback is given after a procedure is completed instead of during it. And this could cause potentially missing critical teaching moments if the juniors had opportunities to have more autonomy. And then also geographical barriers, because in person training requires both parties to be in the same location. And due to the shortage, this is not always feasible.
Um, so NextGen Scrub is an AR-powered platform designed to revolutionize surgical training. With real-time video streaming, interactive annotations, and remote supervision, it enhances mentorship and provides precise competency assessment, ensuring trainees get immediate, high-quality feedback from anywhere in the world. By bridging the gap between in-person training and remote education, NextGen Scrub makes surgical learning more accessible, interactive, and more effective.
What is the impact of our project? Well, there's a lot of interest in this technology. So we are working on this project with Dr. Wang, who's a pediatric urologist surgeon at Victoria Hospital. However, it's not just him who's interested in this. There's plenty of surgeons from neurology, cardiology, orthopedic, oncology, and many more surgical departments that are waiting for this technology to be implemented because they really need it. So much so that this project is actually funded by the Laverne Catalyst Grant under Peter Wang. The implications of this are even bigger than just overcoming geographical barriers in surgical training. This will improve learning retention and training autonomy, which then will enhance surgical precision with the real-time feedback. And through this, it will reduce training costs compared to traditional methods. And almost the biggest one is that we will be helping more competent surgeons be produced at higher rates.
So NextGen Scrub is built around 6 key features that make remote surgical training possible. The first one is live video streaming, which allows a trainee's field of view to be shared in real time with a remote mentor or remote senior surgeon. Through interactive annotations, the mentor can mark up the video feed, guiding the trainee with precise visual cues. And the annotations are also recorded so trainees can review them later for self-assessment. Two-way communication ensures that both parties can discuss the procedure in real time, making the interaction as close to an in-person mentorship session as possible. To make the training experience even more valuable, the platform records the entire session, which includes video, audio, and annotations, so it can be used for future learning. Most importantly, all of this is done remotely, meaning the mentorship is no longer restricted by location. And by combining these features, GenScrub makes the surgical training more interactive and scalable. So let's walk through a typical training session of NextGen Scrub. A training session starts with the trainee wearing a HoloLens, which streams a view to a remote mentor in real time. The senior surgeon, who is watching from a tablet, can annotate directly on the video feed, and these annotations appear as visual markers in the trainee's HoloLens display, giving them immediate guidance during the procedure if needed. Two-way communication to ensure both parties can discuss what's happening in real time. And again, this entire session will be recorded so the trainee can review the procedure afterwards. And this whole thing is also a foundation on the future AI implementation for evaluation. This allows for real-time mentorship and post-procedure learning to make training more effective.
Next, let's talk about some design challenges that we faced during our project. To start us off, here's a little quote which says, "If you fail to plan, you plan to fail." This is kind of what we experienced when we first inherited this project, because this project was not started from scratch. There were previous student developers working on it. However, they had some significant issues with it. Firstly, the communication architecture was set up so that it was from HoloLens to HoloLens. So annotations were done by the senior surgeon through their HoloLens and then casted to the junior's HoloLens. This ultimately was not the architecture that the stakeholders wanted, so that would have to be changed. Next, the project used model-based rendering, which meant that the goal was that the HoloLens would read the topography of the patient and render that into a model and cast it over to the next HoloLens. Beta testing was used a generic model for this, but again, this was not the ideal methodology. And lastly, and perhaps the most important flaw, was that the precision of the annotations were very, very low. They had poor accuracy and poor precision and were nowhere near the minimum required for the surgery. Due to this, we had to redefine the requirements, which involved having multiple meetings with all the stakeholders involved. And through that, we established four main goals. The first one, the communication architecture, we were going to change that so that the junior surgeon would have a HoloLens, the senior surgeon would have a tablet, and then they would communicate from HoloLens to tablet. Next, instead of creating a model of the patient with their topography, we were going to use video-based rendering. So we just had to broadcast a video of the junior's view to the tablet. And then the annotations would be done on the tablet by the senior surgeon to ensure higher precision. And overall, we just wanted to go back to the basics. So what this means is that all the unnecessary functionalities, such as sign-in, account verification, session rooms, and color coding different incision types, would be removed. Once we had redefined our project vision and goals, we had to consider what restrictions we had on the designs. So first of all, the HoloLens, they made an announcement, Microsoft, that they would be discontinuing them by 2027. So this meant that the future usability of the lens was uncertain, and we would have to consider continued development, including the eventual migration to other headsets. And then in terms of the HoloLens and its capabilities, it had some restrictions such as the resolution. It needed a minimum resolution of 1080p. It had performance constraints of operating at 32 frames per second, with any change in that leading to very significant lag, which would be noticeable by the user. And lastly, there were connection security issues with different networks having different firewalls in place, which we then had to consider how we were going to bypass these or handle them. And this leads us to a better quote. So a clear plan today is the foundation for a successful project tomorrow.
Now we're going to break down the process of actually developing the project. Here we have the implementation tools used. The HoloLens primarily operates on the Unity game engine, so we use that along with Microsoft's mixed reality toolkit for most of the development. Photon was used for the video streaming and the live annotations. In Unity, programming is done in C Sharp, so that was programmed using Rider and Visual Studio. The code was maintained on GitHub for version control. The Android development tools were used for the tablet deployment, and the screen recorder, as seen there, was used to save sessions. Going generally over the functionalities in the order in which we did them. First, we did the annotations. That was our biggest concern coming into this version of the project, as they were the biggest issue in the previous version. Um, then we did the HoloLens to tablet communication. That's very vital to the project, as the remote telementoring is the baseline. After that, we did the timestamping and tracking. The future of the project is very reliant on the data that is gathered from these sessions. So, tracking annotation data is obviously very important in that regard. Then we did the live video feed. That's another huge feature that's essential for the senior surgeon annotations, as he would be unable to figure out where his annotations were without it. And then finally, we did the recording of sessions. Again, for the future of the project, as those sessions can be used as training data for AI. Now, to discuss our overall development process, I'm going to use our annotations as the feature example. So first, we would design the feature. So we would figure out what was wrong with the previous version of it or what we needed to accomplish. So in this case, the annotations, we were working off of a previous version, and we decided that they were not accurate or precise enough. So that was the main goal of our design. Then we would implement this design. And once implemented, we would test that design and its features and whether or not it accomplishes what we intended. So whether or not it would be accurate enough in this instance. After that, we would present the feature to our advisors for their critique, and their critique would be used to inform the next version of the design. And then that cycle would repeat, obviously cyclically, until we were content with the feature.
So let's go over what went right and what went wrong. Firstly, what went right? One of our biggest successes was moving annotations to the tablet, which improved the precision and usability. Um, we added a color wheel to give the senior surgeons more control and making guidance more clear. Switching to video broadcast instead of the rendering of 3D model on the 3D model made the system faster and more efficient. And by saving annotations, we created a foundation for future references by the trainee and senior surgeon and allow for future AI-powered assessments tools to be developed.
Apart from the technicalities, other things our team got right was our organization. We took lots of meeting minutes and we made sure to plan features extensively before trying to implement them. Communication was good as well. It was often, and we made sure to avoid misinterpretation using many questions. We were very adaptable. As said before, we had to rework an entire version of the project. So that was obviously very adaptable, as well as the many libraries and frameworks we had to go through in making specific features, such as the video streaming. Teamwork was good as well. We made sure to depend on teammates when needed, and we divided the tasks very evenly to avoid burnout. We also proved meaningful applications and impact as we exceeded project requirements, and we are preparing for the next step by testing in a cadaver lab.
We did have some challenges. The first one being platform differences among team members, which caused compatibility issues, as some of us used Mac and others used Windows. And this really slowed us down as it made it harder to integrate our work efficiently. Our voice transfer feature wasn't as smooth as we wanted it. It works, but because of all the other information that we're transferring through the server, it slowed everything down and is unable to process it properly. We also had some networking problems and server limitations that led to the occasional lag. And finally, annotation visibility on the tablet needed adjustments to ensure clarity.
And other than the technical problems, um, more so in general, as we discussed before, in the first semester, there were a lot of misunderstood objectives from the previous code base and previous conversations with the stakeholders. And so this caused us to inherit a project that had a lot of technical debt. We had to go back and restart and redesign and code even basic features, basically from the ground up. This turned into a lot of misallocated time of redefining those features and restarting those features that we had initially thought were all done. And this led to time constraints because by the time that was all finished and we had a clear plan and vision for our project, it was January. So that only gave us 2 months to code and implement our features.
Now moving on to the actual demonstration of our product. Here we have the HoloLens on the right and the tablet on the left that it was deployed to. Here we have a video on an older version of the software showing the annotations, how they can be drawn, as well as the ability to change their color. And here we have a image of me wearing the HoloLens. Uh, the HoloLens camera is picking up the picture of the book I'm looking at and displaying it to the tablet on the left. Notice the high quality of the video being picked up.
So, as Malcolm mentioned, the resolution and the clarity of the camera view from the HoloLens to the tablet is something that we're really proud of. It is a resolution that's even higher than HD, and Dr. Wang was very, very impressed and happy with the results. This video shows how you can change the color of the annotations on the tablet side according to whatever you would like. And this video shows how on the left, somebody can be annotating on the tablet, and that processes real time and shows up on the HoloLens side.
Here are some photos from the trainee surgeon side. As you can see, the annotations are shown through the HoloLens screen, and we'll show you a video of it working live. We had a hard time. We had a hard time putting our phone camera to show the HoloLens view, but it looks a lot better when you're looking at it through your naked eye. So as you can see here, the annotations are transmitted to the HoloLens screen. The function of the annotation is for the senior surgeon to point out or outline a specific area for the trainee to see if needed, and it will be recorded into a CSV file for future reference, and the annotations disappear automatically after a few seconds. And here's an example of a CSV file that contains all of the information about the annotations. It has the timestamp of when it was made, the annotation number, the color, and the XYZ coordinates. And this will be automatically downloaded into the computer for the future reference.
Now that we've discussed the important features in detail as well as their implementations, now we're going to break down why they matter, their long-term meaning, and the future of the project. So a quick summary of the main features we'd like to discuss more. The remote video streaming that displays the feed of the junior surgeon's view. The video quality is very high, as mentioned earlier. It's higher than HD, so that means more than 720p. That allows for high precision and accuracy, which is very important for a surgery setting. Those video sessions are saved and used for review, but More importantly is their data. We'll get more to that in a second. And the other main feature is live annotations to direct the junior surgeon. Those are obviously drawn over the junior surgeon's view. They are customizable in color for their differentiation, and that annotation data is saved as well for later use. So what? The main use of all these systems will be creating data to train AI with the video recording of surgery sessions and saved annotation data. AI can obviously do a lot with that data. So here's some good examples of what it can be used for. First, we have enhancing surgical training. So AI would be able to analyze recorded surgeries and their annotations to assess a junior's performance. Evaluating their performance can help identify strengths, their weaknesses, as well as whether or not they adhere to procedure. Another idea is improved knowledge transfer. So this will facilitate a remote mentorship as the future surgeons can learn from the expert annotations over the real surgical footage. And the coolest one is likely the AI mentorship, where AI can eventually fulfill a similar role to that of a senior surgeon, where they can make annotations over live surgery itself. That has the potential, obviously, for AI mentoring and training, which will free up more senior surgeons. Our project NextGenScrub is more than a tool. It is a step towards the future of surgical training. We're very excited that we could be a part of such a huge milestone in surgical tech, and we're very thankful that you could listen, and we'd love to hear your thoughts. Thank you.